So we finished our discussion of Snell's law talking about a situation in which we said the index of refraction in medium 2 was less than the index of refraction in medium 1, which told us that the refracted ray was going to bend away from the normal. The thing to notice, of course, is that there is a limit to how far away I can bend that ray away from the normal, right? At some point, if that ray is going to continue to be transmitted through into the second medium, there's only so far that I can let that ray bend away. So there is a limit to what theta r can be, what that refracted angle can be. And that's given by what's known as the critical angle. So this only occurs when the second medium has a lower index of refraction than the first medium. And so the refracted ray is going to bend away from the normal. But since the refracted ray tells us about the transmitted piece of the incoming ray when it hits that surface, once it's basically going out along the surface, I don't have much of a transmitted ray anymore. And so this corresponds to the situation where the incident angle is at the critical angle because the refracted angle is 90 degrees. And so this lets us define what the critical angle is for the interface between two media. Because of course, once we get past this critical angle, what we're going to see is we end up with total internal reflection. The critical angle is the largest angle your incoming ray can make before all of the ray gets reflected back. So if we start with Snell's law, again, I've got the index of refraction for the medium in which my incoming ray sits times the sine of, well, that incident angle in this case is the critical angle. That's got to equal the index of refraction for my refracted ray, in this case medium 2, times the sine of the refracted angle, which we just said is 90 degrees if we're at the critical angle. Well, sine of 90 is just 1, and so I can solve this for the critical angle. And I get that the sine of the critical angle is equal to the index of refraction where the refracted ray is trying to enter over the index of refraction of the incoming medium. So in this case, for this particular picture, this would be the index of refraction for medium 2 over the index of refraction for medium 1. Because the index of refraction for medium 2 is smaller, right? It has to be for our refracted ray to bend away from the normal. This ratio will always be less than 1. Since the sine of any number has to be less than 1, that makes sense. So we only get total internal reflection in a situation where we're going from a larger index of refraction into a medium with a smaller index of refraction. Well, once you go past that critical angle, again, so here's the critical angle that we just calculated. Once you go past that so that your incident angle is now greater than the critical angle, what that means is there's no place more where your transmitted ray can bend away from the normal. It was already bending as much as it possibly could when it was being transmitted out along the surface. By going to an incident angle that's greater than the critical angle, there's nowhere left for it to bend, and so all of your incoming ray now reflects back. So this is why you get total internal reflection. This is actually a really important property because transmission lines, coaxial cables, the way fiber optics depend on this being the way things function, so that you can minimize your signal loss by having total internal reflection. None of your ray goes through into the second medium, and so you keep all of your signal in that reflected ray.